right, so today we left off last week in here talking about functions and function notation. And we're going to talk a little bit today, review wise, about what makes something a function versus not a function, some other sort of relationship. But then I would like to spend most of our class time on today is playing around with GC a little bit and doing some cool things with that, using function notation as a part of that. So GC will allow you to not only do computations and draw graphs, but we can also draw moving objects. We can make them move and demonstrate change, which is kind of essential for talking about calculus, measuring rate of change, or if I know rate of change, how do I figure out what happens because of that? It helps a little bit if we can envision something that's actually moving. So some quantity increases or decreases, and what happens in the other related quantity. Like if x grows, what happens to y and how? And if we can see that happening, it's easier to describe and think about the changes in or the variations in the two related variables. So part of all of this, though, is understanding what makes something a function, because if you try to use function notation with something that isn't a function, you get some kind of unexpected results or unusual problems. But this is something that I'm guessing you talked about in earlier classes, probably anywhere, any variety of algebra. You talked about what makes something a function, whether it's like an intro algebra, intermediate, or algebra 2, or a college algebra class, maybe pre-calculus as well. But if I have an independent quantity and a dependent quantity, or even if I just talk about two co-equal sort of quantities that are related somehow, what makes that relationship a function? Can anyone remember something that you learned about what makes a relationship specifically qualify as a function? Or anything you look for? Yeah.
If the graph passes the line test.
Okay, so yeah, there's a vertical line test to determine whether something's a function if you're looking at a graph of it. So what's the deal with the line test? How do you pass the line test? Yeah.
It has to be a one-to-one function, meaning one input gets one output.
Okay, so one-to-one function is actually a subset of functions, but yeah, one-to-one means every one input gives you one output, and vice versa. So if I give you one y value, there's only one x that goes with that as well. So something like a parabola, thinking graph-wise, passes that vertical line test because any one x value and like y equals x squared, just thinking of a basic one, there's only one answer that you get from squaring an x value. However, it's not what's called one-to-one, which we'll talk more about that a little bit later, not necessary for what we're doing today. One-to-one would also mean if I tell you the y value, then you know which one x value that pertains to. If I'm thinking y equals x squared and I say 9, like, ooh, well, that could have come from 3 or negative 3. So it is a function, but one-to-one functions are a special subset of functions, which are nice to work with because it does go both ways. But yeah, for functions, for any one input, the independent variable, whatever is declared to be that, and typically that's graphed on the horizontal axis, there's only one y value or one output that's given, one dependent quantity that you get as a result. So if I say something like, oh, this function relationship is described by a function called f. When I say f of 3, that's one number because for any input like 3, there's only one answer. If f were something other than a function, I said f of 3, maybe there's a couple different values it could have even if you have the formula to calculate it by, the function rule. So yeah, something that's a function notation is very useful because by putting in that one input as a part of that function notation, you know the output. It describes precisely one value. So the dependent value quantity or the output is uniquely determined by the input, meaning if I tell you the input, that's enough to know the output. So in any case, looking at an example, if I can get this to go. If you're making a phone call, and I say, okay, you're making a phone call, let's declare an independent variable in this phone call situation. It's not going to be a formula to follow. Independent variable is going to be the phone number that you're trying to call. Now, these phone numbers probably would require some additional, on modern phones, 3 digits so that it knows who you actually want to call. But suppose that the phone number that you're dialing, whatever it is, these fit in an oval, is your independent variable. What would be the dependent variable? dialing one of these, or no dialing either, pushing the symbols for these would get what? Well, you'd get a recipient of some sort on the other end of the line, you hope, or just nobody's answering, possibly voicemail. But your hope is that you get one particular person or place or business on the other end. So if your phone is functioning properly, then when you dial enough numbers, you get one specific person. So if I dial that number, I get Visa customer service or whatever it is. Or if I dial this other number, I get my friend all the time. I don't sometimes get my friend and sometimes get Visa customer service, just depending on the whims of my phone. That would be bad. So a function, in any case, this, as it's drawn right here, is drawn as what we were just talking about. This is a one-to-one function. Every one person corresponds to one phone number and vice versa. The fact that this is a function is that every one phone number describes precisely who you're going to get, and you only need to know the phone number to know who you're supposed to get, or what. It doesn't necessarily tell you who at Visa customer service you get, but it tells you whose phone number, who should be on the other end, generally speaking. So for each value of the independent variable, the value of the dependent variable is uniquely determined. So uniquely determined just means that there's going to be one and there's only going to be one dependent variable based on having a value, any value of the independent that fits in the domain. So if you had that number and you dialed it, if sometimes you got mom and sometimes you got pizza delivery, that's bad, correct? That's not a function, or in terms of this description up here, for each value of the independent variable, this phone number, it doesn't uniquely determine in this situation. So that would be not a function relationship. It'd also be a malfunctioning phone. Same with any other pair. But if you do have something like this, this is okay. So if your friend has two phone numbers, like the landline in the kitchen and their cell phone, and you can try to get a hold of them two different ways, that's perfectly okay, because each independent variable, each of the phone numbers chosen uniquely determines exactly one person on the other end that should be picking up the line. So this is okay as a function. This still fits the definition of function. This is like the parabola situation. Two different x values give you the same y value. That's okay, as long as it's not the other way around. The one x value, one phone number gives you, kind of depends who answers the phone. Malfunctioning phone, not a function. But this situation is okay. I just want to point this out with a kind of silly example other than just like parabolas. But that's okay. And Visa customer service probably has multiple different numbers, so that would be okay. You know, this situation is okay. If one or more independent variable values end up having the same output or dependent variable value associated with them, that's okay in a function. The other way around is, in general, something that can happen, but it doesn't describe something that's called a function. And like I said, the reason we're concerned about this isn't because it's not allowed to have, like, you don't want your phone to do that for sure, but in terms of the usefulness of function notation, it's useful for things that are actually functions, so that when I say f of 7, that describes precisely one value, the value of the dependent variable when the input is 7, which should be one thing, not multiple different things, just kind of depending on something else. So that's why function notation is useful for functions. There are other relationships that aren't functions, and they're not bad in general. With a phone, it would be bad. They're not bad in general. It's just that function notation would not be as useful with those, because by declaring something like g of 3, if that could be a couple different things, then saying g of 3 doesn't describe enough what you want to say. So let's talk about using function notation to describe things, even when I don't have a formula or a way to compute. So I'm going to leave this up here for a little while. I hope it's big enough to see, but I'll read through it in any case. The very top says, let t equal the time elapsed in seconds since a race car began moving after a pit stop, and let capital D represent the distance in feet traveled by the car since it first started moving after the pit stop. Sorry, I suppose I should say that. So the phrase D is a function of t means the value of D is uniquely determined by the value of t. So thinking about that and what we were just talking about, there's two statements, A and B here. So the first part A, I'm just going to read them and then think about them for a minute. So the phrase D is a function of t means the value of D is uniquely determined by the value of t. In that statement, which quantity is independent and which is dependent? And then part B, using a function named W, represent distance D at any number of seconds t. So think about those two statements. I'm going to ask for volunteer answers to either of them in a minute, but I know especially if you're in the back, that might be a little hard to read. All right, so the phrase D is a function of t. In that statement, which quantity is independent and which is dependent? Anyone want to take a guess? Or a no? Yeah, sure.
The independent is D and
Independent D, dependent T. I think we've got that backwards. So this D is a function of T. Another way to say that is D depends on T. And so if that's a helpful, different phrase, this one's used a lot in mathematics books. It says y is a function of x. And if you think about, oh yeah, that's the way it normally goes. And y is the outcome and x is the input or the starting point. D is a function of t. You can also say that as D is dependent on t. So in reality, this relationship can go either way. This is likely an example of a one-to-one function, unless the car stops, but it's not likely to in the middle of a race after the pit stop. So if this D is a function of t, that means D depends on t, or if I knew t, I could predict or compute or calculate a value for D somehow or another. Now we don't have a formula to do that by, but what we do have, and let me start up this guy maybe. There we go. And let me also move this. It's kind of in the way. No, it doesn't want me to move it. Sorry. Stubborn doodad. So I could write D is a function of t. If I use the function name W, would it be W parentheses D, W of D, or W of t that makes sense then, corresponding to what we just said? W of t, right, so D is a function of, function's name is W, t. D equals W of t is something that you can write. In generic math examples, often you'll see y equals f of x. Y is a function of x. And you can almost kind of just read that like pretending that function of is f for function. That's why it's used. But D is a function of t. If the function name is w, we'd write D equals W of t. So t determines D. Time determines, if I give you a time, that determines how far it's gone, or distance is dependent on time. Time is the independent variable. Now, just as a math science sort of thing, lots of the time, if time is one of the elements of a relationship, it gets to be the independent variable because we generally don't get to control time. And so it's more normal to explain a relationship in that way because time just kind of goes on. But we can always rearrange an equation to have it solved for something else if you have an equation. But this, the way this is said, I'd say D equals W of t. All right, so let me get out of this for just a second, try to get my doodad writing. This little gizmo is acting up on me today, including my keyboard. Hold on. Do this the hard way. All right. Start. Maybe? Hold on just a sec. So I do want to write this for you, and it's being stubborn today. really, really quit. All right. All right. Sorry about this. Here we go. Just get back to where we were, and then I'll put the screen back up. It's being very stubborn, making me click on everything. There we go. Now, maybe. There we go. Oh, and now it's in the middle of the screen. It's even worse than it was before. Come on, buddy. Well, I apologize. This is not going to cooperate today, so I'll just have to do this the old-fashioned way on the board. So I just wanted to get it on the recording somehow. But in any case, the phrase D is a function of t means that D depends on t. So thinking about that, this question number 2 asks us to represent a few different things using function notation with function W, and D and T are related to by W. So if I wanted to talk about the distance traveled by the car after the first 9 seconds using function W, how could I express that? I don't know what that distance is, but what notation would indicate that distance? Yeah. W of 9. Yeah, so W is this relationship between the distance traveled by the car since it started moving after the pit stop, and T is the time since it started moving after the pit stop. So if I want to know the distance after 9 seconds from the pit stop, the first 9 seconds here, so it would say W of 9. Make sure it's not D of 9. So W of 9 is a value of D, distance, but W is the relationship that has the input T and output D. And W is the name of the relationship. So this would be W, okay, yeah, W of 9 would give us that. Now, what if I wanted to know the change in the total distance traveled between time 2 and time 5 seconds after this pit stop? Or in other words, if I want to know how far it traveled during that interval, or the change in the total distance. Yeah. W5 minus W2. Yeah, so if I want to know a change, thinking like that dy, y final minus y initial, I hope that sounds familiar from last week. So in this case, final is 5 seconds, and initial is 2 seconds, and we want to know the y values at those 2 times, or the output values, or the distance values. Now, as a question, W of 5 minus W of 2, how does that relate to W of 3? Are they the same? I mean, I suppose they could happen to be the same, but they don't mean the same things. This tells us the difference in these distance values between time 2 and time 5. W of 3 would mean what? Distance after 3 seconds, which could happen to be the same number, but there's no reason that those have to be the same. So just keep in mind that with function notation, don't do x final minus x initial and get the y value from that, because that tells us something else. That would tell us in this case, it wouldn't even know that we use 2 and 5 versus 1 and 4 or 7 and 10 or anything else. It just says, oh, 3. And if you put 3 into or as an input for function W, it's saying, oh, 3 is a value of time after the start of, or after the car started moving after the pit stop. So it's not using a particular interval of time, it's just using that as if it's a value of time. So to get the variation in the distance, or the change in the total distance traveled between those 2 points in time, we do need this subtraction to do that. Now, thinking about that, the distance traveled by the car after the first 9 seconds, part A, there's another way that we could write this, because it is actually a change in total distance, where we just happen to have known one of the values, so maybe didn't even think about it. What could I subtract from this and it would be the same? Yeah, W of 0. So because of the way that these variables are defined, W of 0 would have to have the value 0 because it's distance after it started moving. And so W of 0 would be 0 seconds after it started moving. Despite the fact I don't know a whole lot about this, it hasn't moved yet, so that would be distance 0. So that part A could be W of 9 on its own, or to make it kind of think about it the same way as we did with part B, it could be that subtraction. All right, now C and D, I'm going to read these and let you think about how you want to write these for a moment, but C says the additional distance traveled by the car during the second 4-second time interval after it started to move. So think about which seconds those are and how you'd express the distance traveled during that second 4-second interval. And then part D, the additional distance traveled during a 7-second time interval that begins at a general time x, t equals x. So again, these aren't things that we can compute that distance, but how could I express those or represent those with function notation? So think about these two. Think about what is the time interval. Because if you can do that, we've got some ideas of how to deal with time intervals. All right, so what about C? So my first question for C, the second 4-second time interval after it started to move. What's the beginning time and ending time of the time interval that we're talking about here? 4 to 8, yeah. So the first 4-second time interval after it started to move would be time 0 to 4. And then right after that is the next 4 seconds, 4 to 8. We don't have to skip over and say 5 to something, because there's a whole second in between 4 and 5. But just thinking about continuous timer on the number line, like 0 through whatever, the first 4 units is that first 4-second time interval. The next 4 units starts where the first one left off. So this would be the interval 4 through 8. I want to know what happens to the distance traveled between the beginning and the end of that interval. So how far in total the car traveled during it would be the distance traveled difference between where it was at time 4 and where it was at time 8, or the distance traveled by time 4, distance traveled by time 8. So that's function notation W of 8 minus W of 4. All right, so what about for part D here? What interval are we talking about if I were going to try to write out the time interval? A 7-second time interval beginning at a general time x, t equals x. Almost. So the interval starts at x, right? And it needs to be a 7-second time interval. Yeah, so 7 plus x, right? Because I don't know what x is. If I want something that's 7 seconds later than x, then the end of the interval would be x plus 7. That guarantees it's 7 units long. But again, I can't just use the 7 seconds and say, oh, W of 7, because that would be how far the car had driven in the first 7 seconds or where it was at time 7. And that's not what I want. I want to know how far it traveled during a general 7 seconds that starts at mystery time t equals x. But if we can do this, we can just translate this W of x plus 7 minus W of x. So y final minus y initial. And again, the final is using x final. The y value when the x is at its final spot relative to question D situation. And W of x is the y initial. because x is the initial, the start of the interval that we're interested in. All right, so this computing change is something, or this variation over an interval, the difference between the beginning and end of an interval is something that we're going to do a lot in here. So just be familiar with this if you think, oh, I need to know the difference in the output or the difference in the y values, the difference in the dependent variables. Think about this subtracting function notation. That is going to be used quite a bit. So speaking of that, take a look at number 3. There are A, B, C, D, E, F, 6 different expressions using W's with various input. I'll read through them because I know some of it's kind of small. There are 6 different expressions with this function W. I'm going to try to come up with a story about them related to the car and driving and number of seconds and that sort of thing. So the first one says 2W of A. B, the second one, says W of C minus W of 8. Part C says W of 7.5 minus the number 9. Part D says W of 3 plus H minus W of 3. Part E says W of T plus 10 minus W of T. And then the last expression says W of X plus 0.5. Did I say the W? W of X plus 0.5 minus W of X all over 0.5. So take a couple minutes, look at them, discuss with your neighbor. Could you make a description about this car and driving in time that somehow relates to each of those? And there's a variety of different answers in some cases. It's not like, oh, there's only one way I could interpret this. It's not a lot to go on. But I know what function W does, and I know what the input values mean. Think about your units and how you describe this. And what units might make sense in the case of things that are just numbers tossed in there in order for you to do a computation. All right, so what about this first one? 2W of A. Any descriptions of something that might make sense related to a car about that? 2 times the distance at A seconds. So the units on this would be, if this W is the function as described above, what sort of units would be on this? Feet. So we have, 2 times the number of feet that the car traveled in the first A seconds, or the distance after A seconds. There's a times 2. So I don't know what that 2 might be, but probably the most reasonable thing is to say, oh, just twice that distance. So maybe one car went W of A feet and a different car went twice as far, 2W of A feet in that A seconds. What about part B? That looks maybe sort of like a familiar setup from previous questions. What could that represent?
The distance traveled between
Yeah, the distance traveled by the car between time 8 and time C. So this would be final final minus initial, so this would be an interval from 8 seconds to C seconds. Yeah. And this would give us our distance in feet. If part C is to make any sense, maybe that's something similar, only we happen to have a number for the initial distance. That wouldn't be 9 seconds. If I'm subtracting these, I probably wouldn't be doing feet minus seconds because that'd be kind of weird. Feet minus a number of cats. Now, if this is feet, then if I'm going to do this operation, I hope that I'm subtracting another number of feet so that it makes sense. But this would be, I don't know, what could you describe that would make sense for this?
Distance at 7.5 seconds minus 9 feet.
Yeah, the distance at 7.5 seconds. So maybe it's 7.5 seconds into the race. This is how far one car has traveled, and there's another one that's 9 feet behind it. So its distance traveled is 9 feet less. But this is 9 feet less than W of 7.5. Maybe that 9 feet is, its position at mystery time. We just don't have a letter for it. But in order for this to make sense, that 9 would probably have to be something about feet. Part D, W of 3 plus H minus W of 3. So that's again one of these subtracting two function notation expressions. So we can talk about it as a change in distance or a change in position of this car when. During what interval of time are we concerned about? Yeah, it starts at time 3, duration of H seconds. So it goes from time 3 to time 3 plus mystery H, but that makes the interval exactly H seconds long. So this would be how far it travels in that particular H second interval starting at time 3. Good. All right, now what about E, W of t plus 10 minus W of t? It looks kind of similar to the last one. There's mystery numbers in there. How long is the interval of time that we're concerned about in part E? Yeah, it's 10 seconds. So this one was, the duration was H seconds. And this one, the duration is 10 seconds. But the starting point is the mystery, time T. Kind of like this one that we did on the board, where it was starting at mystery time X. All right, so part F looks similar to B through E, subtraction of a couple of quantities. We hope that it's subtracting feet to determine some sort of distance traveled or a difference in distances. It's over 0.5. There's a few different ways you could interpret that that makes sense. Multiplication and division you can do with any sort of units you want. So it doesn't have to be something about feet. Any thoughts on what that might be? Almost. So dividing by 0.5 would be times 2, twice the distance traveled during that interval. So we could do that. Now we're actually going to see expressions like this for a completely different reason. So in part A, there was a times 2. This could actually have been rewritten as a times 2, 2 times that quantity subtracted. But it could also be, notice that this is an interval of 0.5 seconds. If I divide by 0.5, I could think of that as 0.5 seconds. And if this is a number of feet traveled in 0.5 seconds, and I divided it by 0.5 seconds, I get the speed in feet per second as an average distance traveled in a certain amount of time. So that could give me speed during that interval as an average, like a single number speed. But again, it could be a lot of things. Like I said, it could just be twice the distance traveled during that particular time interval that starts at time X and lasts for half a second. But like I said, there's room for interpretation on especially this one and even that 2 at the beginning. You could do the reverse with that. Say, oh, it's divided by 0.5 and do something with that. So in any case, function notation can be used to represent quantities even when we don't know their values, as long as we have a good definition of the function and the variables that are used for the input and output, the independent and the dependent quantities. So let me move on to something else. can find it. Do it this way. All right, so I just want to talk about GC a little bit on here, and then we're going to open up GC and do something together. Just starting from a blank slate, typing in some stuff. But just a little bit of note. I hope you had a chance to play around with GC a little bit over the weekend. Maybe you talked about it a bit in recitation on Friday. But GC, we did just some type in some stuff, define a function, then you can evaluate with it. Just a few things about it that make it a little bit tedious at times, but is very nice in other cases, which is why it was done. If you type symbols X, Y, or Z, it automatically starts thinking ooh, you're trying to draw a graph in the regular Cartesian coordinate system, 2 or 3 dimensions, depending on if you involve Z or not. These you probably wouldn't type quite so lightly, like theta and P, R is something you might just type. But those are similar. Those are reserved for graphing in polar, spherical, and cylindrical coordinates, which you'll deal with a lot of those in Calculus 2 and 3. T, U, and V are related to parametric equations. They're usually perfectly fine to write unless you just start writing X equals or T equals. If you type something like that, it wants to start drawing a graph for you. And if you're just trying to define a parameter value, it won't like you very much. It'll start graphing instead of, if you write T equals 3, it's going to draw you a graph instead of making T some parameter with a value of 3. So just try to avoid using X, Y, Z, R, and T. Once you accidentally just maybe think of typing as parameters that you're assigning values to, because it doesn't like that. N does something else, which is kind of cool. This is how we're going to be able to animate things. It's the built-in letter. You can also create other things that make moving parts by defining sliders as a function. It's kind of like a little computer programming-ish trick. You just say slider equals, and then you get to define it. But N, by default, will say, ooh, this is a slider. What I mean by slider is it makes a little draggable bar at the bottom, and you can, if you use the symbol N in an equation, you can change its value by dragging the slider around. So you can make a variable vary at your own kind of rate. There's also a little play button that shows up, so you can just kind of push it and watch things change and not have to be physically dragging a little slider bar. E and I and pi, you can't redefine them as anything else. Those are like E is the 2.7 Euler's number, I is square root of -1, and pi is 3.14. But I'm guessing that you wouldn't try to use those just offhand. So in GC, there's a file that's in Canvas that you can open up, but let me just open up GC really quick. So just to point out, with pi and other Greek letters, if you type them, if I type P-I is how it's spelled in English, I guess. But if I type P, it says equals 1. That means, ooh, I'm ready to have this be a parameter. Until you assign another value to it, it's going to be 1. If I type I, it changes into the letter pi and tells me the value of pi, at which point I don't get to assign a value to it. It's 3.14159. Not exactly, but it is in this document. If I were to just use it, it would use it rounded to that position. There's some settings you can change, document settings, and this is set to round off decimals to, or numbers to 6 places. So just 6 significant figures is what it uses. But you can change that to something else. If I change it to 8, then I can see more of pi. But just for sanity purposes, it doesn't spew numbers all the way across the screen. So yours, by default, when you download it, I believe is set to 6 significant digits, meaning even large, extremely large numbers, it's not going to show you all, like if you have things in the millions and billions, it's likely going to give you scientific notation pretty quickly and round off the end things. It won't say 1.4279308. Again, won't have the decimals all the way across the screen. It'll give you the 6 significant figures, but leave it in scientific notation so that you can know how large this is. So in any case, if I wanted to graph something, based on what we were just talking about, if you use y's and x's and write equations, it'll start graphing things in GC. So if I were to type something like y equals x squared, and to get squared, just the caret key that's above the 6 makes this jump up into exponent position. And as soon as I start typing this stuff with y and x, it says graph down here, if I don't hit enter, it won't do a graph. But if I try to do another line, it'll suddenly show me a graph anyway. So I'm just going to click graph, and just a couple of things. This graph is not in a particularly convenient spot. You can click on the axes and drag them around. So if your graph is like kind of what you want to see, but it's just off to the side, you can drag it a little bit. You can also zoom out and zoom in. These little mountains down here, I can never remember which is what, but one is zoom out, probably this one, yep, and one zoom in. But you can also do one axis at a time. So if I want to make it like see more vertically, but without spreading it out horizontally, I can zoom in and out one axis at a time, and it's different from computer to computer type, but the kind of bottom left-hand side of your keyboard buttons, like function, control, command, if you push those, some of those will make little arrows pop up. On my Mac, it's the option and the command button that make little arrows pop up where the mountains are. And if I hit on mine it's option, I can just go squish left to right or stretch it left to right without changing vertically. So I can, see more of the axis and make the parabola narrower or vice versa. There are other ways you can just kind of manually set the window. It's not precise like a TI calculator is where it cuts off the window exactly where you say, but under the graph, you can set your range, like your minimum and maximum. This is X min, X max, Y max, Y min. That's under, feel free to look around, check out these menus up at the top, but the graph menu allows you to manually set the range, and it'll kind of set it. It's not going to be like snap precision to the edge of the graphing area, but it more or less gets what you type in. I was going to say, if I hit the command key, or I think it might be the window key on the Windows machines, I forget which one it is, you can just zoom the other axis. Leave one axis alone and zoom on the other. So this way you can get a graph to be a reasonable shape to fit in a window, or you can focus on certain parts of it if you want to look at something more carefully. And what I want us to look at is, let's see, on Canvas. Oh, by the way, while I have this open, it doesn't show on here right now. It will on Thursday. There's going to be a quiz that's online on iMath that'll be open from Thursday, not all day, but from like 3 p.m. to midnight. You can do it at any point in time. I'll remind you again on Thursday and put it in an announcement as well. But you'll see there'll be a few quizzes that we do in iMath AS that are just, it's probably like a 10-15 minute quiz at most, but just it's basically questions similar to the homework, but it's not set up where, like the homework is, where you can try it multiple times and see whether you're right or wrong. It's just put in your best answers, hit submit, and you're done, and you'll see the grade after the deadline's passed. But there will be one that's coming up that'll be available Thursday afternoon through the end of the night while I have that open. But on Canvas, I did add some things to the main page for you to be able to see, and this is at Module 1. So the box cost problem, I thought I had that up before, but apparently I had it half hidden or something. Sunflower example. This is what I'd like for us to do today. So if you want to open it up on your computer, you can have your own version of it. I'm going to open it up just for fun. It's a PDF, and you can just look at it here. You can download it outside of Canvas. It's really, I know you can't see my version of it right here, because this is really tiny. But let's see. I'm going to make this a little bigger so that I can see it. And where's my, there we go. Get rid of some stuff. So what this is, and I have this on Keynote as well, but it might be just as easy to look at here. There are parts A through F of things to do. And I want us to kind of go through these together, but it's looking at a cubic function, a cubic polynomial, that we want to define as a function in GC and then do a few things with the graph. We're going to put on a coordinate point to highlight a specific dot and draw some kind of like guidelines up from the axis to that point. And then we'll talk about sliders a little bit, just so you can see what I mean by those, and I'll show you a couple different things that we can do with those. So, in any case, the height of the sunflower, I don't know if can I zoom this in? Quite blurry, but here's our height function here. Now it says h of t equals negative 0.1 t cubed plus 1.7 t squared minus 0.6 t for t equals 0 through 10 days. Now, if you go into GC, sometimes it depends actually on your version of it and your computer's operating system. But if I want to graph this function, there's two steps to doing that. One, I have to tell the computer what function h is, what the relationship is, and then I'm going to use y and x to get it to graph that. And I'm going to graph, like we talked about earlier, y equals not f of x, but well, whatever I called it. I can call it h, I can call it something else if I want. But I'm going to define the function using function notation. That way I can refer to specific y values without having to separately calculate them someplace else. So I want to define this function, and so let's just make one command line in GC that says h of t equals, and you can type it just like this. I suggested in A to use x as a placeholder because I know you can use any letter you want as the, like h of m equals negative 0.1 m cubed. It doesn't really matter what letter you use when you're defining it. When we want it to graph, it's going to be x. And some computers are just touchy about t, although x seemed to work on all of them the last time I went through this, as when you were defining the function. So let me just get my GC back. Negative 0.1, 1.7, negative 6. So if you open this up and just have a blank, something like this, and case matters, so if you use a capital H one place and then refer to it later with a lowercase h, it's not going to know what you're talking about. So make sure whatever symbols you choose to use, just make sure you're consistent with capital or lowercase. So I'm going to write h of x, like I said there. Oh, and I did it wrong. So when you're defining functions, if I just hit parentheses, notice there's kind of a big space there, and if I type something like 3, it starts computing this. So this isn't defining a function right now. This is, and you can see if I try to delete one of the parentheses, it's got a time sign that it's putting in there. If you want to define a function, you need to use the control button and then the 9, so it's like a alternate parentheses instead of shift 9 to get the left parenthesis. It's control 9, and notice how the parentheses are kind of more sucked right onto the h. There's not a time sign sort of space in between. But if I type 3 right now, it's not computing anything. So that means, it's not doing multiplication. It knows this is going to be a function. But I actually want to define a function with not 3 in it, but h of x. And the function was negative 0.1, which you don't have to have the leading zeros, but it always makes it easier to read, so you can't miss the decimal point if there's a 0 in the front of it, times, in this case, x cubed, x to the 3rd power. What was it, plus 1.7x? Oh, yeah. And then minus 0.6x. Okay. So if I just hit enter or hit anything right now, it's not going to graph this because this isn't instructions to graph. All this line does is this defines a function. So from now on, if I use capital H, it's thinking, ooh, you're talking about a function. I'm waiting for an input or I'm waiting for something to do with it now. So this is define the function. And so any place I refer to H on the same window of GC, it's going to know that I'm talking about this function here. It doesn't have to use the letter X again. In this, in this function here, that x is just a placeholder that's defining for whatever you want to put in that spot later, whether it's another letter or a numerical value is up to you. So if I want another command line so that I can tell it to do more stuff, I'm going to hit the command button or control button, I forget which one it is on a PC, and then return, and you should get another square of some sort of color. And it doesn't matter what color it is, but if I leave it red and I'm doing something graphical, it's going to show up as a red graph. So if you want to change the color to something else, and you can decide that whenever you want, click on the square, change it to one of those other colors. The X'd out, that's to make it invisible. So that way, if you have something graphed and you have, like if you have multiple things graphed and you want to hide some temporarily without deleting what you typed, you can just make it invisible using that X thing. But I'll just leave this as red. So what I want to graph is, I want to have the Y be the dependent variables, the values of h of x, and x be x. So I'm going to tell it to graph by doing y equals, and then capital H. And once you've defined a function, and I type this H, it already knows functions, so whether I hit Shift 9 or Control 9, it should do it correctly. Yeah. So if I say y equals h of x, it's got y's and x's, and it says, ooh, that's something I can graph. So I can hit graph, and it looks like this. Now, this was supposed to be the height of a sunflower at X days after the seed germinates. So probably to the left of 0 isn't really of interest. And in fact, if you look back at the instructions we had here, have GC graph the function h on the intervals 0 through 10. And then I'm going to make it show up in the screen and just ask you to kind of do the same, but that part C is just about zooming. So I want to graph this on the interval 0 through 10. So to tell GC to graph just part of this, not the whole function on, well, it's a polynomial, domains all real numbers. If I just want to graph this on 0 through 10, on this same line where it says y equals h of x, this is the line that is the command to graph it, I'm going to put a comma, and then I'm going to state my interval. Now, unfortunately, I can't use interval notation. I'm just going to use less than sort of notation. So 0 through 10, 0 is less than or equal to x is less than or equal to 10. Now, in reality, less than and less than or equal to in this graph are going to look exactly the same. See if I can remember how to get a less than or equal to with keys. It's like control less than, yeah. Yeah, control shift less than. Sometimes when they update things, it changes what buttons do what, so I apologize for not always knowing which buttons do what. And I also have a PC in my office, and so I get super confused between going back and forth between two different operating systems where the buttons are named different things. But adding that to the end means it's only going to show the graph on that interval. So I can just hit graph again, or I can hit enter, return. Now this looks kind of weird that it's negative, but just thinking about, okay, so this is a planted seed. It's a little bit underground, so that's only for the first 0.4 of a day or whatever that it's underground or height less than 0. But after that, this seems to make sense. Now if I want to zoom out so I can see 0 through 10, I can play around with these zoom things, like, oh, I need to go from 0 to 10 and see all of that, but this isn't helpful. I need to see more vertically. So what I'm going to do is kind of drag this over here, because I don't care what's to the left. I don't need to put it all the way in the corner, and then figure out how to make this go spread out left to right. So clicking on these buttons, like, nope, that's top to bottom. Ooh, spread out left to right. This one. So that I can maybe see some more of this, but now it's a little bit too far and I can't see all the way up to 10. So it's a little bit of fussing around with this to see the whole graph. Ah, there we go. So I can see 0 through 10 on the x-axis, and then the height you can see goes up to 60. Now, like I was saying earlier, if you want to play around and set the XY visible range here, you can try it that way, like say, oh, I want to see 0 through 10 and 0 through, I don't really know. You can try it that way and then just expand the Y using the buttons down in the bottom left to zoom in and out. But once you can kind of see the graph, you can also get to zoom in a variety of different ways. So in any case, like I said, this shows up as red. If you want to make it black, you can click on black. If you want to make it disappear for a minute, I can click on this X box. Now it's not gone, it's just hidden as if it was in the way and I didn't want to look at it for a minute because I was trying to focus on something else. So this is showing here. Notice that there's no purple box next to the other line anymore. That's okay. You can't, once you've entered it in, it's not going to come back unless you're clicking on that line, since it's not a graph that you can change the color of. There's nothing purple or whatever color you might have had about the function h of x in general. But so what I want to do is take a look at how to graph things other than whole functions. So if I want to graph a single point, I need to tell GC to graph a single point, and it's not done with like xy parentheses. It's done as a vector in reality. It's like matrix looking notation. So again, in the instructions, the next step was, besides zooming around, part D, have GC plot a dot on the function graph to highlight the exact correspondence point, the xy point. It's called correspondence point because it's time and height. There's a corresponding pair of values there. But we want when the independent variable, which would be the x variable, has a value of 4.245 days. So let's just look at this point where it's 4.245 days. I'm going to get a new command line hitting like command enter. And it'll make my graph go away for a little bit. If I want to see my graph, I can hit graph again. But if I want to have a coordinate point, I can hit this 2 vector, or it's like shift 2 to do it, or whatever button is. Yours looks different if you've got a PC. But this math, this 2 vector thing that shows up, this is just like a coordinate pair. It's a single spot for x, a single value for x, and a single value for y. Or you can also put representations of things there, meaning I wanted this to be exactly at 4.245 days. I don't know what the height of the function of the sunflower is there off the top of my head, and I know what the formula is for it. I could compute that, but guess what? I don't need to because I'm using a computer right now. I can say, oh, well, what's the y value? It's h of 4.245. Whatever it is, that expression there will compute it. I don't have to compute it separately and then type in a decimal number for it. I can just use this point 4.245, comma, thinking like if you're writing xy pair, h of 4.245. Those are the corresponding pair. You can tell by the notation. And when I hit graph, I can see, well, I have a blue line with a red dot on it. That's right around 4.25. And it's exactly on the curve. It's not just kind of close to it because of how we type this in. Now, if I had, this is kind of tedious function. We could have calculated out, and if you're curious and want to know what is h of 4.245, you can have GC do that. 4.245. It's 20 point something, but remember the document settings. This is possibly not the whole number. It could be just, it could have like 3 or 4 more decimal places. It's just a polynomial function, so it's not going to go on forever. It's not anything irrational. But it should be at 20 point something. But the thing is that I don't have to calculate that out separately. I can see that, oh yeah, that seems to be in the right spot. But notice, if I wanted to know, well, what is it at 4.247? As long as I change the y value to go with it, it's still exactly on the curve. It's just a slightly bigger value. But I could change the xy point to be at any location I wanted to. So one of the things, let me put this back to 4.245. The next thing on the list of things to do, just to play, this is just exercises in playing around with GC, as well as getting used to function notation in maybe a different way than you've used it before, just not worrying about what the numerical output values are, but just writing the expression for it and leave it at that, because this is a computer program. It can work out all that without you having to do it separately. So here, there's my graph again. If you ever have that graph is just a blue button in the bottom and your graph is gone, if you just hit enter, it'll come back. All right, so the next step was to draw some lines. And we're going to draw actually not full lines, but line segments. So we're going to highlight that spot. So we have a red dot, or mine is red, yours could be a different color, in the middle of this sunflower height curve. And what I'd like to do is kind of point at it. So have a vertical line come up from the x-axis and go to that point, and a horizontal line come across from the y-axis and go to that point, just so you can kind of see it more clearly, because sometimes individual dots are easy to miss. So if I want to emphasize it or point it out, I could draw some lines that go to it. So think about, let's see, back to GC here. If I want to draw a vertical line that goes from the x-axis right up to this point, equation of a vertical line, what's that generally look like? Yeah, just x equals something. So if I wanted to go to this point, it would be x equals what number? 4.245. All right. And let's see, let me get to my end here. Actually don't need that line in there. Just random computation. But if I want to graph x equals 4.245, I can just type that. You don't have to do anything fancy because it's a vertical line. Now this is actually going to give me the whole line. If I want to make this just go from the x-axis up to that point, just kind of similar to what we did with the sunflower, just graphing it from 0 to 10, can you figure out what expression you need to write after a comma to only have the part of that line that starts at the x-axis and goes up to the curve? It might be trickier than you think. Have to use a little bit of trickery to get it to be exact. So what is it that I'm restricting here if I only want this portion? Is it, am I restricting x values or y values to a limited interval? Y values. So the y is going to start at 0 and go through 4.245? Is that the y value here? H of 4.245. Yeah, good. So we can use function notation to tell it where to stop that line. So comma, 0, let's see, less than or equal to y, and h of 4.245, if I can type right. So this is that y value that's 20 point something, that's at the end there. And again, it's like, ooh, that green's really hard to see. Let me make this a different color. And black blends in with the access. Let me make it purple. There we go. So see if you can do the same thing, but with a horizontal line segment extending from the y-axis across to that point and being exactly the right height. So another command line. I'll put the graph back. I just hit enter so it show the graph again. If you get little miscellaneous error messages like that, they'll go away once you do something else. You don't have to try to delete the error message. But horizontal line is going to be an equation, generally y equals some number. What number do I need? Y equals h of 4.245, right? And that's the whole line. Now all I have to do is restrict it so it's just from the axis to the point, since that's what the instructions were. There's no like general rule in life about that's how line segments work. But I'd restrict x or y? X. So x is going to be between 0 and 4.245. All right, so comma, 0, x, 4.245. Again, it's like control shift less thans. But in reality, if you just do the less than without all the extra buttons, it looks exactly the same because there's no like mystery like circle versus dot at the end that appears. There's no end marks on these. The only way you get dots is if you tell it to draw a dot. So let me make this something a little bit darker. There we go. So we've got the horizontal and vertical line segments that go from the axes out to this point that was at randomly chosen 4.245, comma h of 4.245. So this just kind of emphasizes that point. Now, last thing I wanted to show you today is sliders. So that's cool and all, but it would be niftier if I could kind of not just have a single point, but maybe I want to look at all the points and be able to drag this point along this curve and look at the corresponding x and y values. So by having these lines, it kind of makes it easier to read across and go, this is about 4 1/4, that's a little bit more than 20. Now this one's pretty close to some grid lines, some lattice points, so it's maybe easy to estimate that. Some of the others may be harder to see, and especially the farther you get from the axes, the harder it is to see. If I wanted to make a point that's movable, I don't want to put in a specific value of x and y. I want to put in a general value of x and y, and I'm going to pick n to be this general value because n makes this something I can physically slide with my finger. So instead of 4.245 and h of that, I'm going to have n and h of n as my coordinate point. Now, after typing in this stuff that involves n, this little extra bit at the bottom shows up where I can drag the slider across, and it happens to go from 0 to 10, and you can move the dot back and forth manually, or you can hit play, and it'll just do this over and over again. Now those lines aren't moving. They're still at the place we left them, but we can adjust those in a second. If your slider is doing something weird, or if you're making one for a specific document, this one just happens to have used the default settings. If you click on this N, it lets you change some settings. So mine says lowest value 0, highest value 10, which that works pretty well with this graph because that was what we're looking at anyway. We're looking at x values from 0 to 10. This number of steps, basically, this isn't actually sliding smoothly along. It's moving the pixels 100 different times between 0 and 10. So it's only really stopping every 10th of a unit. And if you look at the values here that show up at the right, it shows you the value of n, but it's just going up 1/10 of a unit at a time. It's actually kind of a jagged jumping, but when you play it quickly, it looks like it's moving smoothly. So that number of steps is, like, if I picked a larger number, and there's a limit to how large you can do it, but if I pick a larger number for number of steps, it'll, like 400 I think is the max. Now I can have more accuracy in stopping points, and it will look smoother, although move more slowly because GC does the computations at a certain rate, but it looks more smooth. So instead of going only every 10th of a unit, now it's every, I don't know, 1/4 of a tenth. 2.5% of a unit. So you can change those settings if you want to see a little bit something different. But what I'd like to do is have these two nice lines here move along with that point. So in the point, I changed it from 4.245 and h of that to changing those 4.245s to n's, so that it wasn't that one specific spot, but so that's a movable spot, anything from 0 to 10. If I do that throughout, change all the instances of the number 4.245 into n's, it should change everything to move that way. So I don't want x equals 4.245. I want it to show x equals n, where it's going to go from the axis to h of n, which has a little bit of a problem right at the beginning because, as you remember, the height was negative for the first 0.5, so this would be nowhere, but that's okay. And y equals not h of 4.245, but h of whatever the x value is, where the x value, I want this to extend across from 0 through whatever n is. Now I've got a whole moving demonstration of a lot of different things here. So I can view the point, I can slide that manually. I can look at this, I can think about, well, here's, maybe the beginning of an interval. I'm going to change this back to 100 steps. So it's just tenths, easier numbers to deal with. So if I'm at n equals 7, oh, 7, that seems to be at about, let's see, 40, 45, 50. Okay, so those are by 5s. So 7 goes with about 45. Probably not exact. I can click on the graph and see what the point is in decimal form. 7 looks like 44.8 on this, which is only 3 decimal places, so that's probably exact. But as time increases from 7 days to 8 days for the sunflower, the height increased from 45 to looks like 52 or so. I can see more exactly. Say, okay, 52 point, that's a lot of digits, so that's probably not quite exact, but it could be. I can say, oh, well, that grew by about 7.4 inches or something over a period of 1 day. So it's growing during that day. Its average growth rate's about 7.4 inches per day. Earlier on, its growth rate might have been smaller. Or I could look over small intervals, like, from 3 to 3.1 or 2 days and see, like, okay, so how much did it grow in that small amount of time? I could talk about its growth rate, finding its rate of change. Because if I look at small enough sections of this, and I'm going to shift and then click to draw a rectangle. If I look at small enough sections, this looks pretty much like a straight line segment. So I should be able to describe constant rates of change at least during small intervals of time. So this is from 2.85 days to 3.15 days, so 0.3 of a day. I don't know how many hours that is. But do you think the sunflower's growth rate changed drastically during that 0.3 of a day? Not really. This looks like it was, the ratio of increase vertically to increase horizontally looks about the same throughout this, meaning just eyeballing it, it looks like a straight line, which would indicate a fairly constant or close to constant growth rate over this interval. Although I know this is actually a curve, over small sections, the curvature isn't changing very much. So I should be able to describe the, visually speaking, steepness. Context-wise, I should be able to describe the growth rate of the sunflower at various moments throughout this 10-day time period. I can't use one number for the whole thing except for maybe to say an average, because clearly if I zoom back out, this was not growing at the same rate all the time. Slowly at first and more quickly. I can see the curvature. It was a cubic function, but this is what we're working on this semester. So I'll stop at that for today. I just wanted us to get a little time to play around with GC in addition to practice with function notation and all the cool things it can do for us, both in writing and on GC. So I will post this a little bit later this morning, so you can see this video again. I will see you Thursday, if not before.